All right. Well, looks like people are able to get in and join us for this. Welcome to the QASIG on Zoom. But thanks for joining this experiment. It's not quite the same as being in person, but one of the cool things is that we get to have our speaker and honored host join us from San Francisco. So that's something we wouldn't have been able to do before. His name is Heemeng Foo, and he's going to be giving a talk.
Okay. Jim was going to introduce you first.
On machine learning and testing. I'm going to turn this over to Jim, who's going to be our host tonight, and explain a little bit more about what's going on. Jim?
Yeah. Hi guys, Jim Frazier here, Business Development Manager for Quardev. Just everybody's kind of a pro at Zoom these days, so I think everybody knows what to expect. But what we'll do is during the presentation, everybody's mics will be muted. At the end, there will be a Q&A section, and if you have a question, please raise your hand, and then we will unmute your mic, and you'll be able to ask the question directly. We should run for about 50 minutes. Probably okay if it runs a little long tonight. But be sure to think about your questions during the presentation and feel free to engage at the end, and then we will open your mics for you. So that said, Heemeng, I'm going to hand it over to you and let you run with it.
Okay, just let me share my screen. Okay, can you guys see my screen?
Yeah, looks good.
Okay, cool. So thanks, many thanks to Quardev for organizing this and inviting me to give this talk. So this is usually the part that, you know, I get a little annoyed when speakers spend a whole lot of time on, because, you know, it's like blah, blah, blah. But I felt that, you know, it was relevant for me to give you guys a rough understanding of how I ended up, you know, looking at this particular paper, which I'm going to talk about today, and you know, like, how did I stumble into this? So a little bit about me. If you find my accent a little strange, I'm originally from Singapore. I spent 12 years at Yahoo, 6 in Singapore and 6 in Silicon Valley, mostly in our headquarters in Sunnyvale. I've spent about 15 years in the mobile space, and started in SMS, in mobile web, and then iOS, Android apps, and so on and so forth. And more recently, I spent about 2 years at Climate Corp, building the front-end test team and getting us to CI/CD. At this point in time, I'm working on engineering excellence, and I also do consult with the data science team on ML testing, because they needed some help with regards to engineering maturity. Shameless plug here, I run the AI and Testing AI meetup group in the Bay Area. And this was a talk I gave sometime in April. So if you want to look me up, just search for Heemeng Foo on LinkedIn. I'm the only one that pops up. That's one of the reasons I go by Heemeng Foo on a professional basis rather than Chris. And my slides, all my slides, including this one that this talk that I'm giving, there's a bit.ly link for that. So just go to bit.ly Heemeng slides, and you'll find all of them there. So what was my journey in AI and ML? So in graduate school, I worked on genetic algorithms, solving a logistics problem. And there I also took a class in neural networks. And this was, you know, way before deep neural networks, so you can probably guess how old I am. And then at Yahoo, I attended a number of tech talks on this subject, and I was looking at it, hey, this looks kind of familiar. And so I dug in, took some courses in machine learning on Coursera and Udemy. And in 2017, I did some research on into the application of AI in testing. In fact, I have a talk on that, and the deck is also on my SlideShare for those of you who are interested. And in 2018, I started the AI in testing. It was called AI in testing and DevOps meetup group then. We've since changed the name to AI in testing and testing AI. And I did some research into testing AI, just because I had some interest, and I gave a talk on that in a meetup group, so I mentioned previously as well. And then sometime around April, I also did some consulting with the data science team at Applied. So shameless plug again. So the AI in testing and testing AI meetup group. The three of us basically running the show. Myself, I'm the chief. I call myself the chief instigator because I'm usually the one organizing the meetups. And then we have Jason Arbon and Ron Bashir, who was advising and helping with looking for people to give talks in this space. So without further ado, I will, just 1 second. Okay, yes. So this is the talk. This is the first slide. So, the name of the talk is actually longer than what was advertised. It's machine learning testing, survey landscapes and horizons, the cliff notes. And the reason it's called the cliff notes is because, I didn't write the paper, okay? So what happened was, as I mentioned previously, I was doing some research and I came across this paper by these four authors, Zhang, Harman, Ma, and Liu. And you can see the archive reference over here. So those of you who want to look for the paper, just Google the archive reference. And this was published in late December of last year. So I went through the paper and my goodness, it was such a chore because it was like 37 pages long. And for those of you who have ever read survey papers before, you know that you can't just read one paper. You read one and then you get to a reference. Okay, what does this mean? And you go and read another paper to understand what it means and so on and so forth. And I started writing down notes on the paper itself. And one day it just dawned on me, hey, this is actually going to be useful to somebody. And so what I did was come up with this deck so that folks, if they want to navigate this paper, there's something for you to use as like a set of notes. So because I didn't write the paper, I don't really know every single item in the paper. So please do not shoot the messenger. Okay, I read most of the paper. I did not read all the 300 citations in there. I've read like maybe 5% of them. So so there will be parts about the paper that I'm like, I have no idea what it means. Please forgive me for that. But what I've done is to sort of organize the information in some way so that if you have particular interest in one part of the one particular section, you can just zoom in. And what I've done also is in this deck, put in the references, okay? So like say, for example, 23, that would mean in the reference section of the paper, citation number 23, okay? And what I've done is also to organize it such to label in this deck, basically referencing sections in the paper itself. So let's say, for example, section 3 machine learning refers to section 3 machine learning in the paper, okay? Now, to simplify things, I've skipped these 3 sections because I didn't feel that that added a whole lot of value to people who really wanted to zoom in to the material. Okay, so this is the structure of the talk. The first is the lay of the land, which is, to give you some kind of like guideposts or introduction to some terminology, so that it will be easier for you to read the paper. And then there will be a section, what I call the heavy parts or the deep dive, which go into a lot more detail. So this is extremely involved, and because of that, and in the interest of time, I will go through very, very briefly. So if you're interested, please, in any of those sections, please, take the time to actually read the paper, but at least you're able to zoom into the sections that you're interested in. And then the last part, typical survey paper, what are the challenges in machine learning testing as well as opportunities. Okay, so machine learning testing is new but growing. So it started, at least the first paper that was published came out in 2007, but in the last 4 years, there has been a really, really huge growth in the number of papers that have been published. And it's kind of obvious why, because it's only in the last 4 years or 4 or 5 years that the interest in machine learning as well as deep neural networks have just skyrocketed, especially in areas of like image processing as well as the autonomous vehicles. And you'll see a lot of references to those in this paper as well. So timeline of research, the first paper, like I mentioned previously, first paper was published in 2007, and then sometime in 2008, we see the first time that metamorphic testing was applied, and I'll talk a little bit about metamorphic testing in a bit. And then, awareness of issues like fairness, and then there were a number of these other milestones like adversarial examples, interpretability, and so on and so forth. Now, I'll cover most of these in these slides. Okay, so a distribution of, so for those of you who do not know, in machine learning, there's the traditional machine learning or general machine learning as described here, as well as the deep learning, which involves deep learning. So that includes things like recurrent neural networks, convolution neural networks, reinforcement learning, and so on and so forth. So as you can see, the growth in the last 4 years has been pretty staggering. And because there have been a lot of implementations of traditional machine learning, it's generally higher, but you can see that over the last 4 years, there's been quite a lot of growth in the area of deep learning testing as well. So this table, from this table, you can see that if, with regards to the interests, a lot of it has to do with supervised learning versus unsupervised, and also in the area of reinforcement learning. Okay, so over here, what the authors have done, which I kind of like, is classify the research into these, let me see, 1, 2, 3, 4, 5, 6 properties. So you can think of them as like properties of like what is it that what aspect of the machine learning algorithm or the machine learning system that you're trying to test for. So there's correctness, robustness, security, fairness, model relevance, interpretability, and efficiency. So you can think what I've done, and you'll see it later, what I've done is classified them into like functional and non-functional requirements, because that sort of resonates with most of us who have been in the testing space for a while. And one thing you will notice is that the bulk of the papers have mostly been in the area of correctness and then robustness and security. But as machine learning matures, and this is something that we have seen in the testing space as well. Once you get beyond like basic functional correctness and all that, right? Then all the NFRs will start to become more and more relevant. So this is another chart that you'll find in the paper. It talks about number of data sets, a number of papers that they found this in, which I thought was interesting. So first of all, most of them, as with most research papers, usually will have just one data set or maybe two data sets. But what was interesting was there are one or a few of them that had 600 data sets for whatever reason. So that was interesting. Okay, so in the paper, there are these 4 tables as well. Basically what they've done is categorize the data sets. And the reason why data sets are so important is because, and that's one of the things that is very pertinent to machine learning, and that is the data plays a very big part in the algorithm, okay? So that's why data sets are so important. Now, for those of you who are familiar with machine learning, what you see is this, for this, the first table over here, data sets that pertain to image classification. You'll see the standard data sets like MNIST, CFAR, ImageNet, IRIS, and so on and so forth. And they also have tables that have to do with NLP, decision making, yes. Okay. Okay, so this is where things get a little more interesting. So before we dive into the material in the paper, there are a few things that I felt were extremely important to introduce upfront. So the first is the Oracle problem. Now in testing, so okay, let me just briefly talk about that. So what's the Oracle problem, right? Testing involves examining the behavior of system in order to discover potential faults. Give me a second. Given an input for a system challenge of distinguishing the corresponding desired behavior. So to explain this, right, so most of us are in the testing space, and what do we do when we write test automation or when we write test cases, right? So we, given a certain set of inputs, we define, or we know what is the expected output. That's how we design test cases and test automation. Now, in machine learning, and this, you'll find this in meta heuristic search as well, where the objective is to optimize, find the maximum or minimum of an objective function. How do you know that you have hit the optimum? So you don't really know. So in machine learning, it's the same. If, say, for example, a n category classification problem, right? How do you know what is the best way of classifying the data? You don't. So that is essentially the Oracle problem. And so to address this, there are a number of techniques. So one of them is metamorphic testing. So what's metamorphic testing? So in order for me to explain, let me give you an example. So so most of you know the traveling salesman problem, right? So given a number of cities, what's the shortest path to take to pass every single city? So let's say you have an algorithm, and you pass in the number of cities, and you get the TSP solution, right? How do you know that's the best? Well, one way is to pick a city, and then ask the city, ask the algorithm, okay, give me the shortest path, the shortest route from the beginning, say for example A to X, and then from X to A again. And the sum of those two should be equal, or should be equal to the optimal path that passes through all the cities, right? So that's basically what metamorphic testing is about. So you define these metamorphic, so-called metamorphic relations in order for you to sort of get around the Oracle problem. So next is differential testing, and there's also a very similar approach called inversion programming. So the whole idea is, okay, let's say you have three, let's say you're testing C compilers. So what you do, okay, you take maybe your GCC, you have your Boolean C, that's how old I am, I still remember what Boolean C, and say Microsoft C. And then you send n number of code, pieces of code, and then you compare the results between the three of them. And then if there is a significant difference between at least two of them, then something is not quite right and is worth investigating. So that's the whole idea behind differential testing. And then adversarial testing, the whole idea is to use perturbed data. So you say, for example, an image, okay? You might perturb the data to basically introduce certain fluctuations in the data and test to see if the algorithm is able to, say, classify it as between a cat and a dog. Say, for example, a typical human, looking at them will most likely be able to distinguish, but you want to, in this case, you want to test the robustness of the algorithm. Okay, another concept that's worthy of mention is this thing called MCDC coverage. So I'm not going to go very deep into this, but essentially, given a set of predicates, right? So say, for example, A and B and C or D, in order to test for every single case, you will have a truth table that is to the power 4. But what is the minimum number of combinations of these set of predicates to cover all meaningful combinations? So I'm not going to go into that, but there is this approach to finding the minimum combination, and you can watch this YouTube video to get more details about that. Okay, so what makes machine learning testing hard? First of all, it's data driven. Okay, so the model behavior changes over time with new data. And in fact, with COVID, right, what's happened is that we had a sudden significant change in user behavior, like almost overnight. Right? And this is actually a real problem that happened with data science teams in the last, I don't know, a few months back, when countries started to lock down. Okay, suddenly their models, had to be retrained because the new, say, for example, retail or travel data all changed, and so that caused a huge effort in retraining their models in order to get more accurate predictions. So it's extremely data driven. So that is one of the key reasons why ML testing is hard. So you have to worry about things like versioning your data instead of just, and also like your unit tests. You need to not just test the code logic, but also factor in the data as well. So things like, sorry for that, I don't know, yeah. You have to version your data so that your results are predictable as well. So we have discussed the Oracle problem, so that's another problem. ML testing, ML is less obvious to modularize, and because of that, testing isolation. So one of the big advances in software engineering has been this whole movement in terms of object-oriented programming, right? In the last 20 years or so. Because for those of us who remember things like COBOL and ALGOL and Fortran, things were not like that a long time ago. You know, you had your dreaded go-to statement, and you know, like in the 70s, you know, with the invention of cyclomatic complexity, people were able to measure the complexity of a piece of code. That there isn't that equivalent in machine learning. So how to address this is still quite an open problem. And the last item is the errors may propagate and become amplified or suppressed. So one interesting thing about real production machine learning systems is that the output of one system may become the input of another. So that causes ripple effects. So if there's an error in a system upstream, that you know the error ripples down to the downstream algorithms as well. And for those of you who are familiar with deep neural networks, you know the problem of disappearing gradient and exploding gradient. So that's also another source of how errors may get amplified or suppressed. Okay, so the paper gives a very nice, actually there are two diagrams that look similar, but they give a very good structure for you to understand the differences between online and offline testing. So the offline process, if you've done any course in data science or machine learning, usually you just cover the offline process where you have data, you come up with a prototype model, you run your model exploration and analysis, and then you come up with one that has maybe the best accuracy or confusion matrix or whatever. And then you deploy the model. But then this is all based on historical data, right? So once the model is deployed, you get more information, and that feeds in to an online testing pipeline. And that and that's where the model gets refined as well. So online testing, there are a number of approaches. So there's A/B testing as well as the standard multi-arm-banded approaches. So the paper also has a very nice and a lot more detailed diagram where there are a lot more parts to both offline as well as online testing, and you can see things like bug triage, bugs identified, and stuff like that in there. This is also a very good diagram for you to understand, like, okay, where do the bugs reside? So if you look at an entire machine learning system, there are parts that talk about that have to do with data, parts that have to do with the learning program, which is the algorithm, and then the framework. So they have basically, let me say classified, but they have sort of grouped the different aspects of the kinds of bugs into those groups as well. And later on, we will be using this structure to basically put the different kinds of bugs into the different bins. Okay, so remember we talked about the properties, right? And I mentioned to you that I classified them into functional and non-functional. So this is where we are now. So correctness and model relevance fall into, in my opinion, the functional aspects. So correctness, they talk about true versus empirical correctness. Empirical because, well, you only have a set of data, and any data is essentially a sampling of what is the true values that are out there. And then model relevance. So I'm not going to go into this as well because this is very involved. So they talk about this idea called VC dimension as well as whether or not complexity. And these both of them have to do with classification, in particular support vector machines. And then you have robustness. How resilient is your machine learning system's correctness? And then security, what's the resilience against potential harm, and so on. Data privacy. So current research focus mainly on privacy preserving and not detecting. So that's another gap that is still a research area. Efficiency, how do we speed up the training of prediction speed? So interestingly, right, the training of a machine learning system, some of the deep neural networks can take a while to train, even with distributed training. Sometimes it is in the order of like days and so on. So that's one area of research still. Fairness, so I don't know if maybe some of you have seen some of these articles where I think it was IBM or one of the companies, they created a sort of AI that predicted whether somebody was more likely to be a criminal or more likely to commit crime, and that AI was extremely biased against people of African American race, and the reason was very simple, because the training data was biased. So that is a huge area of research on how to address fairness in machine learning algorithms. And then the next one is interpretability, and this is also a big area because remember there were all these self-driving car crashes. How do you troubleshoot things like that? For those of you who work on with deep neural networks, it's non-trivial to be able to figure out, like, why is it that it's not working the way it's supposed to be working. But there's a very a good ebook on this, and it's in the link to that is in the paper. Okay. So software testing versus machine learning testing. This is another table you'll find in the paper. And I'm not going to go into too much detail, but as you can see, the first row, component to test, for traditional testing is code, but then for machine learning testing, it's both data and code. So that adds that whole layer of complexity to this. They also have a very nice set of papers where folks have looked into studying open source bugs, bugs from open source projects. As you can see, and most of us in the test space will like, yeah, we've seen this before. Most of it has to do with incorrect implementation. As you can see for the paper from Zhang, TensorFlow, API misuse, and stuff like that. Okay, so this is the part which I will go very, very quickly because, in the interest of time, I think we only have like slightly more than 10 minutes. But in the paper itself, they have classified these sections into like the following: test input generation, test oracles, test adequacy, which basically means coverage, test prioritization and reduction. So for any of you who are or have been test managers in the past, you will know that you can't test everything. So how do you prioritize tests? how do you reduce the entire set of tests to run, and so on. Then debug and repair, general testing frameworks and tools, ML properties to be tested. Remember the 6 or so properties I mentioned previously. So they have classified them into those categories, and then ML testing components. So I will go really, really quickly so that we don't take up too much time. Okay, so test input generation. So they've classified into domain-specific, fuzz, search-based test input generation, symbolic, synthetic data, and so on. So let's go just briefly touch on this. So domain-specific, so basically domain-specific test input synthesis. So 2 categories, adversarial as well as natural, and you can see there are a number of very domain-specific. Say, for example, the GANs. So this is driving scene-based test generation. So you can probably guess this is a self-driving car problem. And then deep billboard, again, this is used for self-driving cars. Audio-based DNNs, this is for testing machine learning that have to do with audio inputs and so on and so forth. Fuzz, for those of you who don't know what fuzzing is, it's essentially passing a random set of data through your system to expose flaws in your code. It's used a whole lot in security testing, penetration testing. But this is also used in to generate test inputs. What's interesting to me is the application of search-based meta-heuristic search, the fuzzing, to generate test data. Okay, symbolic execution. So some of you may have had the opportunity to be exposed to symbolic execution systems. I personally don't feel that this is really that useful in machine learning testing, but there have been a number of papers there. What I find really interesting is synthetic data to test the learning program. Why? Because sometimes you really, really need synthetic data. And those of you who have done test data generation, you know, you want data in a certain format so that you are able to expose bugs for a certain module or a certain component. So the idea is pretty similar. Okay, so metamorphic relations. As I mentioned previously, what metamorphic testing is. So it's widely studied. This is actually one of the big areas of study because, you know, to get around the whole Oracle problem. And so the writers of the paper have classified these papers into coarse grain versus fine grain approaches. And yes, they've also classified papers that have to do with metamorphic relations between data sets and frameworks to apply metamorphic relations. Okay, so cross-referencing as test oracles. So remember differential testing and M-version programming. So M-version programming is a little different from differential programming, differential testing. So differential testing, you have n number of different systems. So say, for example, for classification, you might have a logistic regression, an SVM, a random forest, and maybe an XGBoost or something, and then you compare the results, right? Now in M-version programming, basically what you do is you have different versions of the same algorithm, and you test against that to make sure that the results do not fall too far off. So there's a whole bunch of research in that area as well. And then measurement metrics for designers as oracles. So there's a whole bunch of metrics in there as well. So test coverage. Now, see, in traditional software, you know, what do you do when you want to come up with coverage? You have like branch coverage, line coverage, and so on and so forth. But for machine learning, what do you do? One interesting approach is to look at neuron coverage for deep neural networks. And then MCDC coverage variance. There's some papers, some work in that space. Layer level, for those of you who know deep neural networks, they are multiple layers. Sometimes it's like in the order of 100 of layers, right? So one approach is to test, to look at coverage by layer. And state level coverage, because these apply to recurrent neural networks, because recurrent neural networks essentially have this component of state in there. And then a whole bunch of research that talks about limitations of coverage research. Okay, so test adequacy, I'm going to really go very quickly for this. So there's mutation testing. So those of you who are familiar with fault injection, yeah, so this is similar to that. I wouldn't say it's exactly the same. Surprise adequacy, I'm not even going to attempt to explain this. But surprise is one of those terms that is that's part of I think it's deep neural network. Yes, deep neural network. Deep neural networks. I'm not going to go into too much detail on that. Okay, rule-based checking of test adequacy. This one is really useful. So this paper actually came from Google, and it basically lists down 28 test aspects to consider in the scoring system. So this is really actionable. I felt that this was really useful if you are in charge of a team that's either from engineering or whatever, or from test to use as a rubric for making sure that your system is in good shape. Test prioritization and reduction. Okay, I'm going to skip, but basically you're talking about how do you prioritize and reduce the number of tests. Debugging approaches, I will skip this, but you guys can probably figure out. So basically approaches to debug your neural networks or your machine learning algorithms, and then a whole bunch of these debugging frameworks in there as well. Okay, repair approaches. Now, how do you repair the algorithm? Okay, general testing frameworks and tools. There are a whole bunch of them. I'm not going to go into them. Okay, properties. So you have correctness. Classical approaches would be cross-validation, bootstrapping, and so on. Model relevance. So basically, poor model relevance is usually associated with over or underfitting. Robustness and security. Basically, how do you measure? How do you use perturbation to expose these issues? So whether it's using perturbation of the test data or perturbation on the whole system. Interpretability, we talked about it previously. Yeah, so there's manual assessment or automatic assessment, and then privacy. This one is self-explanatory. Fairness. As I mentioned, this is becoming quite a big area of focus because of things like racial bias and stuff like that. And there's a whole bunch of research in this area. Okay. Bug detection in data. Oh, this is also very big because data is so important, right? You want the data that comes in to your machine learning algorithms to be correct. And for those of you who are familiar with these systems, data quality is like really a very big. Even big companies like Uber have huge data quality issues. And so they usually have teams, just making sure the data is correct. framework for detecting data bugs and so on. Bug detection in learning programs. So unit tests, everybody's familiar with unit tests. Algorithm selection, examination, mutant simulation, program faults. I'm not going to go into that. Yes. So bug detection of frameworks. So standard frameworks like TensorFlow, PyTorch, and so on. They have also studied them and looked at the number of bugs in their number of issues, and also implementation testing of frameworks. Okay, so when we managed to get through that very heavy part of the talk. So we just have 2 more slides, and we are done. So the last section is on testing challenges and opportunities. So the challenges in machine learning testing, first of all, is data. And then, okay, so the challenges, the criticisms have to do with, especially for adversarial inputs, the test data are not natural. So how many, I'm sure most of you, if you're in the testing space, would have had this situation where, you find a bug and then dev comes to you and says, but no user is going to use that. No user is going to do that, right? So in machine learning testing, you have something like this. So criticisms that the test data are not natural. And so there's research in how to make the testing process natural as possible. Challenges in test assessment criteria. So how do you assess different basically a lack of systematic evaluation of different assessment metrics. The oracle problem. So metamorphic relations require some level of human ingenuity to discover. And to some extent, here we go again, flaky tests arise in metamorphic testing. Challenges in testing cost reduction. So for those of you who have ever done some work in this area, you know that it's very annoying to have to retrain your model again and again, especially if it takes hours for it to be trained. And then the other challenge is like low footprint devices. So there's actually a meetup group called TinyML. So this is basically having machine learning algorithms run on low power and low memory footprint devices like your Raspberry Pi. Okay, research opportunities. So more application scenarios, more machine learning categories of tasks, testing other properties, presenting more testing benchmarks, covering more testing activities, mutating investigation in machine learning. Okay, so how to better design mutation operators in machine learning code. But after going through what I've just done, you can see that there's still a lot of areas of research. And so this is actually an area that is very interesting. And that was one of the major conclusions that I had after going through the entire paper. So that is it. Did folks drop off? You're muted, yeah.
I bet this works a whole lot better if I'm not muted. So for all participants, please feel free to ask any questions that you might have either through the Q&A section or feel free to use your hands or raise your hand, excuse me, and then we will unmute you. So Heemeng, we do have first question in on Q&A from Paul Reed, and he asks, how do testing tools respond to model behavior changes over time?
Could you repeat that again?
How do testing tools respond to model behavior changes over time?
So what I've seen, and I wouldn't say that I'm a foremost authority in this, But what I've seen some vendors who have presented their solutions. One of the best, I can't remember the name of the vendor. They have a whole pipeline. I mean, you can actually zoom in to various parts of the machine learning pipeline. And what the system does is they would have captured, you know, various error metrics like your RMS, sorry, is it RMS? Yes. Your error rates or your accuracy. So that would be your accuracy numbers for your model. And when new data comes in, you're able to see that, oh, you know, that has changed. And that triggers things like re-evaluating the models that you want to use. So, and that's one of the problems, right? I mean, if you use traditional testing tools like your unit or even like a sort of like a functional test to test the functionality, that doesn't quite apply because you have to factor in data as well. So I hope I've answered the question. If not, you know, please ask a follow-up question.
Okay. And Heemeng, if you could stop sharing your screen, then I would also have visibility on if anybody's raising their hands. I can't actually see that from right here. There we go. Okay. And were there any other questions via chat, or would anybody like to speak directly? Nothing? Nobody?
I didn't see any others via the chat, so.
Okay. Andrew has a quick question. Shelley, could you unmute Andrew?
Hi, Andrew, you have the floor. Andrew, go ahead. I think you're unmuted, Andrew. You can go ahead if you have a question. Okay, well, we'll pause him for a second. I think Keith has a question too, so let Keith go. Hey, Keith, you have the floor. Oops.
Not so much a question, just I really want to thank you for the talk. I found it very interesting and I'm going to blog about it. I was wondering, do you deal with the AI for Software Testing Association and how does that relate to some of the things that you talked about here?
Ah, yes. So I believe I believe Jason Arblon is on that, right?
Yeah.
So I do regularly consult with him, and in fact, this paper, I got introduced to this paper by him. So he and I are friends on LinkedIn, and one day he posted or he shared an article. He shared a post, and the link for this paper was there, and that's how I got into digging into the paper. Yeah.
Thanks.
And then we also had a question from Paul. So, Paul, did you have a follow-up?
Sure. I noticed that there was a statement in one of your slides that said that there was data that was lacking. One of the reasons that machine learning testing is not where you feel like it should be. Does that refer to the fact that testing data is difficult, or is there specifically not enough data to be tested?
Okay, so I can give you an example because, in fact, one of the sort of side projects I was working on in the last few months was to come up with a to apply machine learning to Jira bug classification. And one of the problems I had faced was that the data was not balanced. So say, for example, you're trying to classify into n bug priorities, so like critical and major and so on and so forth, right? And right, you've seen bug databases. It's never equal. And in order for the machine learning algorithm to really learn, you should have balanced data. So you may not necessarily have balanced data. And so that itself is a problem, right? And then if, let's say, you want to be able to generate data for, say, an image classification problem, okay? Now, deep neural networks, right, you need thousands of data points. Not in terms of hundreds. If you only have hundreds, then use a traditional machine learning algorithm. So how do you generate synthetic data to augment the real data so that your machine learning algorithm is able to sufficiently learn? And in fact, even like in Jason Arbon's, so in Jason Arbon's company, Test.ai, what they do is they basically feed the algorithm a whole bunch of these, mobile UIs, okay, so that the algorithm is smart enough. Say, for example, if your submit button, moves from the top to the bottom or something like that, it figures out, yeah, this is the submit button is over here. But they don't really have thousands and thousands of data points. So they will have to be able to perturb or to modify the data in such a way you have sufficient data to train your model. So whether it's done manually through mechanical Turk or you write code to shift things around, you have to find ways to generate that data. Does that explain your question? Does that answer your question? Sorry.
Okay, Andrew was having trouble with his mic, but he did have a question in regards to supervised versus unsupervised testing. Where the unsupervised testing approaches
right
see more of in the near future.
Right. So interesting that you brought this up. So for unsupervised testing, right? For unsupervised learning, what really works, would work reasonably well would be differential testing. So say, for example, you have a clustering problem, right? So what are the standard algorithms? You have a k-means, you have your hierarchical clustering. But another approach is to use partitioning algorithms or even meta-heuristic search to classify, to cluster, or even something like a genetic algorithm that would work as well. Then you would have some way of comparing the results and arrive at some kind of an idea of how far your algorithm is from what is expected. Does that answer your question?
Andrew, I hope so. If not, go ahead. Yes, he says yes, and thank you.
Okay.
All right. Any more questions via chat or QA? Give everybody just a second. I know we're running a little bit over, so but we'll get your, if you do have any follow-up questions that you didn't get answered, please feel free to send them to us directly. We'll get them to Heemeng and make sure that, that we get your questions answered for you.
Yeah,
And,
I mean, just feel free to connect up with me on LinkedIn. Like I said, just search for Heemeng Foo. I'm the only one that pops up, so that's a nice thing too.
Great.
Okay.
Well, Heemeng, thank you very much for your time. We appreciate it this evening. And
I really hope this was useful, really. And thanks for having me. Thanks for inviting me to give this talk today.
Wonderful talk.
Okay. Hey, Joe, did you have any final comments before we wrap up?
Just thank you for joining us and thank you for the wonderful talk. I appreciate it. We all do.
Thank you.
Okay, thanks everybody. If you have any thoughts, comments on anything that you would like to see different for next round of virtual QASIG, please let us know. We'll try to incorporate that into the presentations. And thank you for joining us. And thanks again to you, Heemeng.
Thank you. Goodbye.
Thanks, Jim, for hosting.
Yeah. All right. Good night.
Thanks, Joe and Shelley, for setting that up.
All right, good night.